My name is Jeff Kuhn. I'm a physicist by training. I got my degree in problems related to studying the sun, and that was back at Princeton back in the early 80s. I moved from there to Michigan State University and the National Solar Observatory in New Mexico, where we continued studies of the sun. And it was in early days, in the 90s, that we conceived of the idea of a very large solar telescope to let us see the magnetism of the sun and to be able to see things that we couldn't see in the 80s from 80s and 90s from the solar telescopes of the day. We couldn't even see it from space because it took a very large telescope to do this. About 25 years ago, I moved to Hawaii, where we thought we had a good chance at building a telescope. We built a small version of the Daniel K. Inouye Solar Telescope for studying the sun's magnetism, and we proved that it could work. And then with collaborators from the National Solar Observatory, we convinced folks that this was the right place to build a very large solar telescope. And so over the last roughly 20 years, this telescope has been in the planning and in the construction. From now, over the last year, this telescope has been operated and is at the early stages of actually collecting scientific information. The big problem that we care about is how the sun changes, because the sun affects us not just because of the energy that it produces, but it affects us because of the magnetism and the storms that interact with the outer part of the sun. So we're in the process of testing and developing instruments that can see that solar magnetism. One of them is called cryo-NIRSP. Another one is called DL-NIRSP. Another one is called VISP. And there's another one called VBI. And each one of these instruments is built by teams of scientists all over the world, from Germany to here locally in Hawaii. The whole project was a massive undertaking. It's about $360 million to build this telescope. And it's taken, as I said, the early planning for this telescope goes back 30 years. The final construction has taken about 10 years here on Haleakala, and we're excited because it's now to the point where it's just beginning to be used. So my research has been affiliated with this telescope over that period of time. I'm also interested in telescopes that can help us understand life in the universe. We think that there'll be a morning sometime in your lifetime when you'll wake up to the news that we've discovered life, maybe even intelligent life, on a planet around another star. And the technology to do that, and the next step in telescopes, is within our grasp, and we think that this is something that can happen in the next decade. That's another area of research that I'm very fond of. This telescope is unique because it sees for the first time the magnetism of the sun outside of the surface of the sun. That's the magnetism that reaches into space and makes its way all the way to Earth to affect us here. So the great advantage of DKIST for us and the discoveries that we anticipate will be understanding how magnetism affects the climate, and it affects the transfer of particles and energetic, we call them coronal mass ejections, and solar storms. That energy and how it makes its way from the sun to the Earth is something that this telescope, and probably only this telescope, will be able to show us. The other great advantage of this telescope is that it's all reflecting mirrors, which means that it can be used to see light that has a long wavelength. It's one of the first telescopes that is very sensitive to the sun, that can see far into the infrared. And so the infrared light that comes from the sun is particularly, it's also sensitive to magnetic fields, but it's a part of the spectrum of the sun that hasn't been very well explored. And we'll use that to understand, for example, how the temperature of the sun changes. The sun has a rhythm of 11 years to it, And that 11-year cycle is the same as the cycle that you know of perhaps as the sunspot cycle. We don't understand that sunspot cycle. The sun is slightly hotter when there are more dark spots on the sun. That's slightly paradoxical. Understanding how the outer part of the sun works and why it gets hotter when there are more sunspots is maybe a clue also to climate change here on the Earth. While there are many influences of climate change, one of them which we know is important are the changes that take place in the sun. And one of the major reasons for building this telescope was to trace how the sun changes in time and to understand the connection of the sun's thermal energy that determines, in part, the temperature of the Earth. So that's a very important part of the discoveries that we expect to make. So I would say that understanding magnetism in the sun and understanding how the sun varies and how it's connected to the Earth are the two great themes for the Daniel K. Inouye telescope. This information that we get from the telescope is ultimately only as good as the instruments. And this telescope has 5 instruments that have been built to take advantage of the very large mirror and the fact that we can see outside of the disk of the sun to the outer parts of the sun. We call that the corona. The improvements that we could make in the instruments include creating more sensitive detectors that let us see the magnetic field in a more sensitive way. And there's already talk of how the next generation of instruments could be used to improve our chances of solving these two key problems. The one is how the sun varies and why it varies, and the other is how is it connected to what happens in the Earth's atmosphere and the Earth's upper atmosphere, and overall, and even potentially in the climate of the Earth. So that will improve with the next generation of instruments, but we're only just using these, and they're such an eye-opener every time these new instruments are turned on to the sun, and it hasn't been that many times. We've only, the total number of new observations numbers in just a few days. As these instruments are understood better and we get more time and experience using them with the sun, we have several years, I think, of discoveries that will be made as we make plans for the next generation of more sensitive instruments. JWST is an incredible advance in the technology of telescopes in space. JWST itself got started in a meeting in the late 1990s. So its time period for development isn't so different than the time period for the Daniel K. Inouye Solar Telescope. JWST is a telescope which is a little bit bigger in diameter than this telescope. The solar telescope has a diameter of 4.2 meters and JWST is 6.5 meters. But JWST is in space, where it doesn't have to deal with the confusing effects of the atmosphere that create turbulence and smear-out images. And it's also above the atmosphere. JWST is undoubtedly going to be an incredible advantage for looking at very distant stars and galaxies, and it will tell us something about the very earliest history of the universe, and we've seen that already. JWST in combination with, for example, LIGO and the gravitational wave detectors are going to tell us new things about black holes and the dense cores of galaxies and clusters of galaxies. They're going to tell us about the history of the universe. They'll probably tell us some things about exoplanets and stars. It's likely that we'll learn something about the planets around other stars and their atmospheres, but it's not really the perfect telescope for that. It's not big enough. It's only 6.5 meters, so it can't collect enough light for doing what we call direct imaging. Direct imaging is the process of being able to see the light that an exoplanet, a faraway planet, reflects the light from its host star. JWST isn't perfect for that, But it will tell us about the early history of the universe, the formation of stars, the formation of galaxies, and it will tell us some things about exoplanets and their atmospheres through the program that they have for doing that. But it's not really what it was designed for. I think the other thing to notice about JWST is it was a $10 billion program. It's a $10 billion telescope. The total amount of money that goes into astronomical research, at least in this country, is about $100 million. So it completely dwarfs everything that we're used to, and it changes the way we do astronomy, which is oftentimes good. It won't be repeated soon. It's a program which, in many ways, is a NASA program that demonstrates technology, and will be hard pressed to have a comparable investment in research dollars from that big telescope. It's interesting that JWST and the Daniel K. Inouye Solar Telescope got their start about the same time and are coming online about the same time, but the scale of the research dollars is almost 2 orders of magnitude different. That's kind of the advantage that we have for ground-based telescopes, is the capabilities of using technologies in ways that achieve some of the same goals for much less cost.